Hi everyone. In this video we're going to look at solving nonlinear systems of equations, particularly those that involve quadratics. So if we have a look here at the system y equals 2x minus 5 and y equals x squared minus 4x, we know that the first equation represents a line and the second represents a parabola. So what we're looking for here are the intersection points between that line and that parabola. And we're going to use a combination to solve these systems, a combination of substitutions, sometimes eliminations, and go from there. But in this case, we're going to use the fact that y has to equal y. So since y has to equal y, that means 2x minus 5 has to equal x squared minus 4x, which means we have a quadratic equation. So that is x squared minus 6x plus 5. This one is factorable. You do also have the quadratic formula if necessary, but x minus 5x minus 1, which means that x can equal 5 or x can equal 1. But that's not the whole answer, because we also do need to consider what are the y values associated with these, and for that you could actually use either of the original equations. So if x equals 5, then y equals 2 times 5 minus 5, or 5 squared minus 4 times 5, either of which would give me 5. And if x equals 1, then y equals 2 times 1 minus 5, which is negative 3, or 1 squared minus 4 times 1, which is also negative 3. So what this means is that my 2 points of intersection are 5, 5, and 1, negative 3. Thinking about this graphically, if I kind of picture in my head what that first line would look like, something like this. The parabola is going to cross the x-axis at 0 and 4. It's going to kind of do this. So my points of intersection 1, negative 3, and 5, 5 do make sense. It is possible for a line and a parabola to intersect twice, once, or not at all. So just like with any regular quadratic equation, we could have one solution, two solutions, or no solutions at all. So considering this one, y equals 2x minus 3 and y equals 2x squared plus 3x plus 9. Same basic idea, y equals y. So that means that 2x minus 3 equals 2x squared plus 3x plus 9. So bringing everything to one side, 2x squared plus x plus 12, which is not factorable because there's nothing that multiplies to 24 and adds to 1. So I would go to the quadratic formula. And in the quadratic formula, x equals negative 1 plus or minus the square root of 1 minus 4 times 2 times 12. I'm not even going to bother doing that multiplication. It would be all over 4, because I can see very clearly here that this is going to be less than 0. Since it's going to be less than 0, there are no real answers, no real solutions. And so that means there are no intersections. And again, thinking about graphically what this is going to look like, going to have my line 2x minus 3 is going to be like that. And the parabola is going to have its vertex at, let's see, negative 3 over 4, somewhere kind of around here-ish, I think. And so they don't intersect, and that is what is going on there. If in doubt, you could, of course, look at a graphing calculator and verify if you're like, maybe I made a mistake and I really should have solutions, but here we don't. We can also have intersections between two parabolas. So again, y equals y, so that means that 6x squared plus 7x minus 4 is going to have to equal 2x squared minus x plus 1. So again, a quadratic equation. So again, I'm going to bring everything over to one side. So that becomes 4x squared plus 8x minus 5 equals 0. And if I look at this one, what multiplies to negative 20 and adds to 8, that would be 10 and negative 2. So this one is factorable. So I've got 2x and 2x, 5 and 1. So I need a positive 10 and negative 2. So the 2x values would be 1/2 or -5/2. And I am then going to substitute into either one of these original equations to find the corresponding y values. So if x equals 1/2, then let's say 6x squared plus 7x minus 4 is going to equal 1. And if x equals -5/2, then when we substitute into either one of these equations, we get y equals 16. So our solution, I need you to actually write as coordinates of a point. So I need you to basically tie together the x value of 1/2 goes with the y value of 1, and the x value of -5/2 goes with 16, and these are coordinate pairs that describe the points of intersection. So one last example, we don't actually even have to be dealing with functions necessarily. So I have a quadratic equation, I have a linear equation. The first one actually describes a circle, and the second one is a line. So we're looking for intersection points between the circle and the line. Again, you can have 1, 2, or 0 intersection points because we are going to end up with a quadratic equation. But here I can't just use y equals y, I'm going to have to use a substitution. So I'm going to take this linear equation and isolate either one of the variables, doesn't matter which one. So let's say x equals y plus 1. So x equals y plus 1, and then I substitute that into the first equation. So I have y plus 1 squared plus y squared equals 25, which means when I distribute y squared plus 2y plus 1 plus y squared minus 25 equals 0, or 2y squared plus 2y minus 24 equals 0. I'm going to divide both sides of this equation by 2 to get y squared plus y equals minus 12 equals 0. Factorable, y plus 4, y minus 3 equals 0, which means y equals -4 or y equals 3. If y equals -4, x equals -4 plus 1, so y plus 1, so -3. And if y equals 3, x would then have to equal 4. So my 2 points of intersection are -3, -4, and 4, 3. And these do work in both equations. That's the whole point. If I square the x value and add the squared y value, I'm going to get 25 for both of these points.